This video is about thin film interference. I did use textbooks from or images from Hina's college physics textbook. I want to give credit there. Thin film interference is a really cool phenomenon. It's why you see rainbow patterns in oil slicks. It's why you see rainbow patterns in bubbles. So let's talk about why that happens. Here's the big picture. We know that constructive interference occurs when the path difference between two waves is equal to a whole integer multiple of the wavelength. And in particular, it's going to be the wavelength of light in a medium, which might not be the same as the wavelength of light in a vacuum. We know that destructive interference is similar, but it's half integer multiples of the wavelength for the path difference rather than whole integer multiples. Our goal is going to be to determine the effective path difference between a reflected ray and one that spends some time in the film, like a bubble, oil spill, etc. And once we have that effective path difference, we'll be in good shape. So before moving on, I want to draw your attention to the image in the top right here. When light is incident on a thin film, like the film of a bubble or the thin film layer on an oil spill, some of that light will reflect, some of that light will refract. Of the refracted light, then when it gets to the air boundary again, some of that will reflect and then refract out, and some of it's going to pass through. So in other words, you're going to get wave interference between the wave that reflected the first time off the near boundary, and that will interfere with the wave that passed through it first and then bounced back, and we'll get some interference patterns. Two factors affect the effective path difference. Phase changes will add a factor of half a wavelength, and the thickness of the film. So overall, the wavelength of light in the medium is going to be equal to the speed of light in that medium divided by frequency. The speed of light in a medium is going to be the ratio of the speed of light in a vacuum to the index of refraction of the medium. A little bit of algebra gives the equation here, and we're left with c divided by frequency is the wavelength of light in air divided by the index of refraction of the medium. So this is going to be an equation that we're going to use to relate the wavelength of light in a medium, the wavelength of light in air, when we're trying to figure out when we get interference. All right. Mechanical waves, like this slinky wave, change phase when reflecting off a fixed end, and they keep the same phase when reflecting off of a free end. This will be important for keeping track of our effective path difference between the two waves. Right here, this shift from a positive to a negative wavelength is as if the wave had shifted half a phase, 180 degrees. It's like it flipped. Whereas here, when this light reflects back, there is no inversion. Thank you to Flipping Physics for these animations. So light does something similar. Light changes phase when it reflects off of a more optically dense medium, and it does not change phase when light reflects off of a less optically dense medium. And so here is the light equivalent to what's happening in the animation on the left. This is the reflection off of a surface with increasing index of refraction, like the air-soap interface for a soap bubble. Your incident wave is coming in, it bounces off, and there is a lambda over 2 phase change, much like the phase change that happens to this wave when it hits a fixed end. For wave B here, when we reflect off a surface with decreasing index of refraction, like the soap-air interface, when we get this reflection from incident wave to reflected wave, there is no phase change. It's like the free end. It's like the free end here It just stays in the same orientation as before. So a soap bubble wall or oil spill in water. Let's look at what's going on there. We've got waves coming in. Here's wave 1 that gets reflected off of the surface. Then here's wave 2, which passes through and then reflects off of the back surface. There is a phase change going from air to soap. There is no phase change trying to go back from soap to air and reflecting. So the effective path difference between the two waves is twice the thickness of the soap. It goes there and back. That's 2 thicknesses. Plus the phase shift of wave 1 at this reflection. So the effective path difference is half the wavelength plus twice the thickness due to the there and back path. So our constructive interference condition is that your effective path length is your order times the wavelength in the medium. The effective path length is half a wavelength plus 2 times the thickness. Subtracting half the wavelength over to the other side of the equation, we get this. And then factoring out the wavelength of the medium, we see that twice the thickness is equal to m minus a half times the wavelength of the medium. And m is any integer, so we can switch out m minus a half and m plus a half. For different values of m, what's in parentheses is the same. And then we end up with an equation that tells us when we get constructive interference. It's when twice the thickness of your soap bubble film is equal to m plus a half times lambda over n. So this is the way to use the thickness of your soap film to tell you when you're going to get constructive interference. Let's say you're now looking at the thin film coating on something like a lens or a window or a windshield. In this case, you're going, you get phase changes at both reflections because you're always going into a more optically dense material. So you get wave 1 reflected off of the surface, wave 2 reflected off of the back surface. Both have a phase change. So our effective path length is the phase shift of wave 1 plus the phase shift of wave 2 plus twice the thickness, which overall the equation looks like this. Add the 2 halves of the wavelength in the medium and you end up with a whole wavelength. The math is otherwise the same. Your path length is equal to m times the wavelength for your constructive interference. The effective path length here is a whole wavelength plus twice the thickness. Subtracting the lambda over to the other side and factoring it out, we end up with 2 times the thickness equals m minus 1 times the wavelength in the medium. But m is any integer, so we can say we can get rid of the minus 1 because that won't change what's in parentheses here since m is arbitrary. And we end up with another relationship for constructive interference. When you're dealing with something like a lens or a window or a windshield, you get constructive interference when twice the thickness is equal to m times the wavelength over the index of refraction. We can summarize this together. And in fact, if we do a little bit of math manipulation, overall, your thin film interference equation looks like this. Twice the thickness is equal to the order of bright spot that you're interested in times wavelength over index refraction divided by 2. This equation works for constructive interference with our soap bubble or oil film. When m is odd, you get constructive interference, and when m is even, you get destructive interference. And then it's the reverse for something like our windshield, where we're always going into an increasing index of refraction. Even m gives you constructive interference, odd m gives you destructive interference. And so the big idea, which I don't want us to lose the big idea in all of the math, the big idea is that we get these really pretty rainbow colors for a very sort of complicated reason. light that reflects off of the back boundary will interfere with light that reflected off of the front boundary. And this creates an interference pattern not that different than the Young's double slit interference pattern that we saw. When interference occurs, where the location of interference depends on wavelength. And so you see different spots where destructive interference is occurring for certain wavelengths of light through varying thicknesses of film. And that's what the pattern is coming from, is different parts of the film have different thicknesses, and then different parts of the film will have different colors being subtracted out. So this, we've got this very thin black line here, where the yellowy orange is, that's where blue is missing. Here, where the blue-green is, that's where our red light is missing, and so on. So the absence of one wavelength of light due to destructive interference gives rise to the pattern we see. That also explains why we don't see all of the colors of the rainbow, because we're not going through all of the wavelengths, we're only subtracting out certain wavelengths at certain places. So that's our end of thin film interference. For AP Physics 2, it is more important that you are roughly aware of the idea than it is that you've got it fully down. This equation in particular is not nearly as important as understanding when phase changes occur and when they don't. All right, that is it for thin film interference.